Hello everyone. Welcome you to week 4 live problem solving session of the course Introduction to Group Theory. I am Priyanka Sharma, your PMRF NPTEL teaching assistant, and I am a research scholar from the Department of Mathematics, IIT Patna. So let's begin with the session. First, we quickly summarize the topics covered in the last week. So these are the main topics. We discussed about cosets of a subgroup in a group and what is Lagrange's theorem, what are the corollaries and some applications in number theory, and what are normal subgroups. So what is a coset? So suppose we have a group G and we have a subgroup of G, say H, then we define a left coset XH as the collection of all elements X operated by H, like this. Similarly, we can define right coset like HX, and obviously the left cosets and right cosets of a subgroup H in a group G with respect to some element X belongs to G, uh, they will differ if we have a non-abelian group. And yeah, XH and HX, that is the right coset and left coset of H with respect to X, they in general differ, but we will have a one-to-one correspondence between them. And we can verify that any two left cosets in a group G, they will either identical or they will be disjoint. And the union of all left cosets of H in G, this will give us the whole group G. But again, as we said that two left cosets can be either identical or disjoint. So yep, there is a possibility that they can be identical. So we need to consider a disjoint union of left cosets of H and G. So that is represented by this. G is a disjoint union of XH, but here the X, this will come from the index set. And if we take in general X belongs to G, then this union can be like non-disjoint. Okay, so how we can find this index set? So we define G over H like this, and then the index set that will be isomorphic to G over H. For example, suppose we have this group R square plus, that is the Euclidean plane, and this multiplication, this additive operation is basically component wise addition. And if we consider the subgroup which is x-axis, then R square H, this will be isomorphic to y-axis. So the index set, that will be the y-axis. Like if we write here, like this R square, this can be written as a disjoint union of X and H, where H is x-axis. Then if we consider this, X belongs to the whole R square, then we will not use this like disjoint operator. No. But if we use X belongs to R square over H, that is, uh, if we pick all points of y-axis, then this union will become disjoint. Now, this idea generates the concept of partition of a set. So when we have a non-empty set, then we can define a partition for it. So suppose X be a non-empty set, then this set A alpha, this will form a partition of X, If A alpha belongs to X, that is, all the A alphas are subsets of X, and the union will give us the whole set X. And if we have this property also, like we are considering the partition. So if we have this, like either two elements from this set are identical or they are disjoint, then we say that the collection A alpha will form a partition of X. Okay. Now, how to define equivalence relation on a set? So again, consider a non-empty set, say X, then a relation which is denoted by this. So first of all, what is a relation? So relation is basically a subset of X cross X. That is, if we have a set X, then the Cartesian product will be X cross X, where we will have elements of the form, say, x1, x2, we can say from this. Okay, so any subset of X cross X, this will be a relation, and a relation will be equivalence relation if it satisfies these three conditions. This is reflexive, this is symmetric, and this is transitive. Now, what these are? So if every element of X is related to itself, then the relation is reflexive. If every pair X and Y belongs to X will give us, like whenever we will have X is related to Y, we will get Y is related to X. So this is symmetric and transitive. So whenever we will have X related to Y and Y related to Z, we will have X is related to Y. Okay. So a relation on a set which is reflexive, symmetric, and transitive, that will become an equivalence relation. Now, if we have an equivalence relation for a non-empty set, then we can have equivalence classes for elements of X. So the equivalent class of X is defined by the set, that is the collection of all those elements of X which are related to X. Okay. Mm, we can see that for any elements X and Y belongs to X, their equivalent classes are either identical or they are disjoint. So this equivalence relation will form a partition. Okay. So we can say, like, whenever we will have an equivalence relation on a set, we will get a partition of the set. And for every partition, we will have an equivalence relation. Like every partition will come from an equivalence relation. Okay. So similarly, this G over H, that is the set of all X, H, these form a partition of G. Now, the next topic is Lagrange's theorem. So what is Lagrange's theorem? This theorem is immediate from this discussion, like uh, whenever we will have a set and we will have a group G and a subgroup, say H, then if we partition and if we get one-to-one correspondence between the cosets, then we will get this. But here we need to consider only finite groups. So if order of G is number of elements in G and order of H is number of elements in H, then by Lagrange's theorem, order of H divides order of G. Okay, it means order of every subgroup of a group divides order of the group. This ratio, order of G by order of H, this is number of left cosets of H in G as well as number of right cosets of H in G. Again, if G is the disjoint union of left cosets of H in G with respect to the element X, then order of G will be calculated by this. So order of G will be the summation of order of this left cosets. Like order of G will be summation of order of XH, but uh, note that here we need to consider this summation for disjoint union. Okay, so here X is not coming from the whole group G. We need to consider only distinct cosets. So X will be from G over H. Okay. Now there are some corollaries of this Lagrange's theorem. So the first one is, if order of G is prime, then G must be cyclic. Okay. And initially we assumed that G is finite. That is, G is a finite cyclic group. Then obviously G will be isomorphic to Z over PZ. The second one is Fermat's little theorem. So suppose we have a prime number, say P, and A belongs to Z, then we have A to the power P. This is equivalent to A mod P. Okay. Or similarly, we can say this as A to the power P minus 1. This is equivalent to 1 under modulo P. Now, we can also see some applications of Lagrange's theorem in number theory. We can verify some well-known theorems of number theory using Lagrange's theorem. So, this corollary is Fermat's little theorem. We can generalize this. Here we consider A to the power P, or to get equivalence with 1, we consider A to the power P minus 1, which is basically A to the power phi of P, right? Where phi is Euler's phi function. So we can say that A to the power phi of P is congruent congruent to 1 under modulo P. But what if we have A to the power some another number? Okay. So that is given by Euler's theorem. So for A belongs to Z minus 0, and we consider this restriction, GCD of A and N, that is 1, then A to the power phi of N is, this is congruent to 1 under modulo P. So this is basically generalization of Fermat's little theorem. And for A belongs to N, we will have this result, and this divides phi of P to the power N minus 1. There are some other results. We quickly revise them. So let G be a group and H is a subgroup of G. Then a function f from G to G dash. Okay, this G dash is another group. So let's write it as, let G and G dash be some groups. Then the function which assigns x to x inverse, this is a bijection. Or like if we are taking inverse in G only, then this G dash, this can be similar to G itself. Okay. So this is a bijection, and image of XH, this will be HX inverse. So under this bijection, we can see that image of every left coset will be a right coset, but the left coset in domain, that if that is generated by X, like if we are considering left coset of H in G with respect to the element X, then its corresponding right coset of H in G will be generated by X inverse, that is inverse of this X. Okay. So this is a way by which we can say, like left cosets and right cosets are uh, like there is a one-to-one correspondence between them. Okay. Now, if we have two subsets, I'm saying in general subsets, not necessarily subgroups. So suppose we have two subsets, K1 and K2 of a given group G, then we can define their product K1 and K1 times K2 in natural way. That is, this is a collection of XG. This is basically X star Y. Okay, here this X is coming from K1 and this Y is coming from K2. So we take care of the order, that is K1 and then K2. So first we will have an element of X of K1, that is X, and then we will have another element from K2, say that is Y. So we consider X star Y, where star is the group operation. So if we collect all these elements, then we will get the product K1, K2. Now this is for subsets. What if we have a subgroup? So this is basically notation for subgroup and this is notation for subset. Okay, so if H is a subgroup of G, then H will be the H itself. Okay, so when we product H by itself, we will get H, or we can generalize this and we can say that H some finite number of times, we will get H again. Okay. To prove this, we can simply consider the closure property as H is a subgroup. Okay. Now, this collection G over H, which is the collection of all left cosets, that is the collection of GH for G belongs to G, this forms a group under operation which is defined by this G1H, G2H. This is G1, G2H. So this is a group, but only if we have this condition, that is GH is HG, that is the left coset with respect to any element, say G, will be the right coset with respect to the same element. Okay, so if we have this condition, that is GH and HG, they are same, then we can say that G over H, that is the set of all left cosets of H and G, and yeah, similarly the set of all right cosets of H and G, they will form a group. But yep, keep in the mind that this condition is necessary. So how to get this condition, or how we can assure that this condition will be there? So the answer is normal subgroup. So if H is not just a simple subgroup, if H is normal subgroup of G, then we will have this condition GH equals to HG always, and then we can define G over H as a subgroup of G. Okay. So what is normal subgroup? So suppose we have a group G and H, which is a subgroup of G, then H will be normal subgroup of G if we have this condition, that is G inverse HG is H. Or we can say that G inverse HG, this belongs to H for all H belongs to H, and yep, for all G belongs to G. Okay, so there are some equivalent conditions for normal subgroups. If G and G inverse is N, where N is claimed to be normal subgroup of G, if G and G inverse is included in N, that is if G and G inverse is just subset of N, if Gn and Ng they are same, that is left coset and right coset, they are same, and if Gn, this forms a group under this operation, all these conditions will give us that N is a normal subgroup actually. Okay, and yep, we can generalize this, like if G1n is G1 dash n and G2n is G2 dash n for G1 G1 dash G2 G2 dash n G, then G1 G2n is G1 dash G2 dash N. And N will be union of G and G inverse. Another equivalent condition is that tau G of N is contained in N. What is tau G? So tau G is inner automorphism of G with respect to this fixed element G in G. So suppose G is a group and we fix an element G in G. Then we define a map from G to G denoted by tau of G such that it assigns any element X in G to Gx G inverse. So this map is an automorphism of G. Automorphism means group isomorphism where we are taking both the groups like the domain and codomain one same. Then the isomorphism will become automorphism actually. So this tau G, this will give us the seventh condition that tau G of N, this is contained in N, and N will be a normal subgroup if and only if there exists a group homomorphism from G to G dash such that N is kernel of phi. That is, we can have a one-to-one correspondence between normal subgroups and kernel of some group homomorphism on G. And the kernel is always normal subgroup. The set of all inner automorphisms is a group, and this is noted by inner automorphisms of G, and this is a subgroup of the group of all automorphisms on G. Now we discuss some questions. So come to the first question. We have 4 statements and we need to check which are true. So there can be more than one correct statements. So the first is a group cannot be isomorphic to its proper subgroup. Second, if there exists an element of infinite order in a group G, then G has infinite number of elements of infinite orders. If third one is if G has an element of order D, then G has a subgroup of order D. And fourth one, if G has a subgroup of order D, then G has an element of order D. That is, this fourth one is the inverse of statement 3. So which one is true, which one is false? So let's discuss them one by one. The first one we have discussed in previous problem solving session. So the first statement is false actually. We can have a counter example. Consider the group of all integers. Say this is G is Z and H which is a subgroup. Let fix it as 2n, that is the subgroup of all even integers. Clearly, G and H, they are not exactly same. H is a proper subgroup of G because there are odd integers in G as well. But we can have a map from Z to 2Z defined by N to 2N, which is an isomorphism. So in this way, we can have an example where a group is isomorphic to its proper subgroup. So the first statement is not true. Second, if there exists an element of order infinite in a group G, then G has infinite number of elements of order infinity. Okay, so let G be a group and there is some A belongs to G such that order of A is infinity, then naturally we can consider the subgroup of G generated by the element A. Okay. So this will be simply I can say subgroup generated by A is a cyclic subgroup of G of infinite order. Okay. So why? See, the set this, which is this is a subgroup. This is clear. Okay. Why this is cyclic and why this is of infinite order? Since this is generated by a single element A, so this is cyclic. And suppose its order is not infinite, then we will get a contradiction to the fact that order of A is infinity. Okay. Order of A is infinity. It means there is no natural number n such that A to the power n is identity, the identity element of the group. Okay. It means this collection A to the power say 0, A square, A cube, and so on. This will form an infinite set, and this is a subgroup, so this will be an infinite subgroup. And this is generated by A, so this is a cyclic subgroup. Now, an infinite cyclic group is isomorphic to this. A will be isomorphic to which group? Whenever we'll have an infinite cyclic group, it can be a unique group up to isomorphism. Okay. And this is isomorphic to Z, the set of all integers mm, with addition operation. Okay. And this, this has infinitely many elements. Order of Z is infinity. So order of this is also infinity, but this is a subgroup of G. That is, G will have at least as many elements as we have in the subgroup generated by A. So order of G will be infinity. So whenever you will have an element of infinite order in a group, you will have infinitely many elements of infinite order in the group. So yes, the second statement is true. Now, what about third statement? If G has an element of order D, then G has a subgroup of order D. So, is it true or false? We have already discussed about this in different ways. So, let G be a group and there is some A belongs to G such that order of A is given as D. Okay. Then we can consider the subgroup generated by A. What will be its order? It will be D. Okay. Because if we have order of the subgroup generated by A less than D, then it will contradict to the fact that order of A is D. Okay. So the third statement is true. Now come to the fourth statement. If G has a subgroup of order D, then G has an element of order D. So is it true? Any guess? Let G be a group and it has a subgroup of some given order, say order D, then is there some A belongs to G such that order of A is D always? So is it true in general? Any of you want to make a guess? Or can we have a counter example to this statement? So a simple, it is one of the simplest counter examples. So consider this. Say the group is Z2 over Z2, or like you can consider it as Z over 2Z cross Z over 2Z. And if we consider H is G itself, okay, then what is the order of H? How many elements will be there in G or in H? How many elements are there in Z over 2Z cross Z over 2Z? What is this? Z over 2Z cross Z over 2Z. This is actually the collection of A, B such that A and B are coming from Z over 2Z. Right. Now, what is the order of this group? How many elements are there in Z over 2Z? Only two? Z over 2Z is actually the collection of 0 plus Z over 2Z, that is only Z over 2Z, and 1 plus Z over 2Z. Okay, whenever you will get 2 plus Z over 2Z, you will get the first element again. Okay. That is order of Z over 2Z is 2. Now the Cartesian product of this order of H, this will be 2 by 2, that is 4. But there is no element of order 4 in Z over 2Z by Z over 2Z. Okay. Why? Because Z over 2Z is actually a collection of these type of elements, tuples A, B, such that A and B belongs to Z over 2Z, right? And order of AB, this will be LCM of order of A and order of B. Fine. But order of A, this can be either 1 or 2. Order of B, this can be either 1 or 2. So order of AB, this can be 1 or 2. You cannot have another option for this. Okay. The order cannot be other than 1 and 2. So the fourth statement is not true. Okay. So the first one, this is false. Fourth is false, and these two are correct. Clear? Now come to the next question. Let f and g be two functions from R minus the set 0, 1 to R defined by f of x is 1 by x and g of x is x minus 1 by x for x belongs to R minus 0 and 1. Okay, so you have two functions. Then show that, okay, I'm giving some conditions, so this not show that. You need to check. Okay, this can be a multiple correct answer. So the smallest group of functions from R minus 0, 1 to R containing f and g under the composition of function, this can be abelian, finite, isomorphic to Z over 6, 8 or S3. So there can be one or more than one correct answer to this question. So first we need to figure out what can be the smallest group of functions containing f and g both. Okay. So group, it means closure property will be there. So whenever the group contains f, all the powers of f will be there. Similarly, all the powers of g will be there. Okay. So let's do it. F is given as this and g of x is x minus 1 over x. Say G is the smallest group containing F and G. That is, F belongs to G and G belongs to G. Then F square, F cube, F to the power 4 and so on, they will be in G, as well as G square, G cube, G to the power 4 and so on, they will be in G. Otherwise, the group operation, which is the composition of function, will not be closed. Okay. So what will be f square? See, the options are the group is infinite. So we need to check whether the group is infinite or finite. So it is actually the question that either all these powers of f are disjoint or we can have a finite order of f. Okay. So consider f square. What will be f square? F square of x, this will be f of x means f of 1 by x. And what is the definition of f? This is basically reciprocal of the element. Okay. So f of 1 by x, this will be x. That is f square of x is I of x, you can say, where I is the identity function. Or all x belongs to G, so not G, what is the domain? R minus 0, 1. Okay. Therefore, order of f is 2. Okay. Actually, we are willing to construct this. So, identity will be there, f and g will be there. Now, if we want to write f square, so that is already included. That is same as the identity. Okay. So, we don't need to write f square. F cube will be f. F4 will be identity again. So this is done. Now come to G. What is G square? So G square X will be G of X, which is G of X minus 1 over X. What will be this? This will be X minus 1 over X minus 1 divided by X minus 1 over X, which is X minus 1 minus X by X minus 1, or minus 1 over X minus 1. Now, this is neither G nor F nor identity function. Okay, so this is something other than previous elements. So G square will be in the group again. Okay, means order of G is greater than 2. Now, what is G cube X? This is G of G square of X, right? What is this? Can you calculate this? What will be the value? Students, am I audible? Hello?
Yes, ma'am.
Okay. So, can you calculate this? What will be G cube X? Actually, your G
Just
cube X. Hmm,
calculating. Just
okay.
calculating.
Okay.
Uh, is it X?
Yes, this is X. Okay. X means like G cube will be the identity function. Okay. Or we can say that order of G is 3. Okay. So order of F is 2 and order of G is 3. It means there is no need to write G cube in this. That is already included. Okay. Now, can we check whether F and G uh, commute with each other or not? What is FGX and what is GFX? Are they same?
Not commitment.
Yes. Uh, okay. And see, in the set G, we already have 4 elements. Okay. So G, F, and FG, are they distinct from those 4 or same? So this will be F of G of X, that is F of, this is X minus 1 over X. Okay. X minus 1 over X So this will be x over x minus 1. And g of f of x. So this will be g of 1 by x, that is 1 by x minus 1 or 1 by x, that is 1 minus x. Okay, so these two are different from the previously included elements. Okay, so fg and gf, they will be here. Similarly, you can consider this like what will be f, like what will be fg square or fg cube, what will be order of fg and what will be order of gf. Okay, so actually there will be only these 6 elements. Okay, so okay, this is false, that the group is not infinite, because order of G is 6 actually. And is G abelian? So no, we have two elements, GF and FG. Uh, Sorry, we have two elements, F and G, and they do not commute. Now, as I said, order of G is 6. So this can be isomorphic to Z over 6Z or S3. But this is an abelian group. So G cannot be isomorphic to this. Uh, G is isomorphic to S3. Okay, which is why this is happening, which is a non-abelian group of order 6. Okay, and actually you can verify this by the order, like how many elements of which order in S3. Okay, and one more thing, there is some elements of order 6 in Z over 6Z, which is the one itself, that is the generator. Okay, but here you will not have any element of order 6, so your group cannot be this. Okay.
Oh, excuse me, like
Mhm.
S3 is a symmetric group,
Yes,
permutation.
yes,
So that,
permutation group.
okay, that you have taught permutation groups like.
Uh, no, actually, we can discuss what is permutation group. Mm,
Okay.
what is S3? So S3 is basically permutation group or symmetric group of permutations of a set of 3 elements. Okay, that is, suppose we have a set X, which is collection of A, B, and C, and we consider all possible permutation, or if we want to number it, say simply 1, 2, and 3. Okay, so S3 means, like, if we want to define Sn in general, so for this we need to consider first a set X such that cardinality of X is n. Okay, to define Sn, that is the permutation group of permutations of set of n elements. First, we need a set of n elements. Okay, now what to do? We define the permutations from X to X. permutations means actually bijections. Okay. For example, in S3, we are taking X as 1, 2, and 3. Then we need to define all permutations. So the first one can be this. I'm writing this as this simply. So this is corresponding to the domain, and here I will write images under sigma 1. So it can be 1, 2, 3 itself, that is the identity, or you can denote it by E. Secondly, you can fix 1 and interchange the uh, 2 and 3. So image of 2 will be 3 and image of 3 will be 2. So this is another permutation. Then we can fix the image of 2 to itself, and we can exchange 3 and 1. So this will be this. And sigma 4, it can be fix 3 and this will be this. Okay. So this is actually this sigma 4 of 1, this is 2. Sigma 4 of 2 is 1 and sigma 4 of 3 is 3. This is the meaning. Okay. Sigma 5. So now what we can do, we can like here we have elements 1, 2 and 3. Now we can shift them in a cycle, like we start numbering from this 1, 2 and 3. Okay. And 1 can be 1, 2 and 3. Okay. So here sigma 5 of I is not equals to I for any I, and same for the permutation sigma 6. Okay. So these are the only possible 6 permutations for this set X. Okay. We cannot have another permutation. Okay. So we can say S3 is now collection of sigma 1, sigma 2, sigma 3, 4, 5, and 6. If we consider these 6 permutations, or if we consider this 6 bijections, then this will form a group. What will be the group operation? So group operation will depend on the nature of elements. Okay. So here the elements are functions basically. So group operation will be composition of functions. Okay. So S3 is a group. Now, in general, sigma 1 is denoted by I. This can be written as 2, 3 also. This can be written as 3, 1, which means we fix 2, but image of 3 is 1 and image of 1 is 3 actually. This is same as 1, 2 or 2, 1. This is actually 1, 2, 3. And this can be, wait, sorry, this is 1, 3, 2, because 1 has image 3, 3 has image 2, and 2 has image 1. And this is one has image 2, 2 has image 3, and then 3 has image 1. Okay, so this is like this. Okay, so if you have a permutation which is given by this, say A1, A2, A3, A4. So it means sigma of A1 is A2, sigma of A2 is A3, sigma of A3 is A4, and sigma of A4 is A1. Okay. And if there is another AIs, okay, then sigma of AI will be AI for I is not equals to 1, 2, 3, and 4. Okay, so this is the meaning actually, and this is the way how we denote. Uh, is it clear?
Yes, ma'am.
Okay. You can compute the orders of elements. So the first one, this is the identity actually, and its order will be 1 itself. Why? Because see, sigma 1 of x is x for all x belongs to x, right? So order of sigma 1 is 1. Now what will be order of sigma 2? So how to calculate? What will be order of sigma 2? Any idea? How to calculate order of sigma 2? See, in this question,
We,
we...
we,
Mhm.
we will apply the composition until we get again the order 1, 2, 3.
Yes, exactly. Like, see, here we have the functions f and g, and we computed their orders. Okay. So, sigma 2, sigma 3, and so on, they are basically functions. Okay. So, using the composition operation, we can find their orders. Or if I give a hint, so what we need, sigma 2 of x is sigma 2 power n of x, like the minimum natural number n, such that like if we apply sigma 2 to itself n times, then we will get image of every element to the element itself. Okay, and this is for all x belongs to x. Okay, so sigma 2 of 1 will be 1, sigma 2 of 2 will be 3, but what will be sigma 2 square of 2? This will be image of 2, that is 2. Okay, and similarly sigma 2 square of 3, that is 2. Okay, so you can say that order of sigma 2 is 2. Okay, so this is the way you can define orders. Uh, these 3 has order 2, and mm, these 2 has order 3. You can calculate. Okay, and you can like if you want to verify, you can also verify this for uh, this question also. Here its order is 1, its order is 2, its order is 3. Uh, I'm leaving this as an exercise for you. What will be order of G square, FG, and GF? Okay. So obviously, 2 from these 3 will be of order 2, and exactly 1 has order 3. You can check. Okay, so is the question clear? And I hope you get an idea what a permutation group is. Okay. Any doubt? So come to the next question. Find the value of 21 to the power 2026 in modulo 11. So how to do this? See, we need to find its value under modulo 11. So its value can be from this 0, 1, 2 up to 10. Okay, because we are considering modulo 11. So we can have 11 possible options for this only. Okay. Now, how to do this? We don't need to find the exact value. Okay. We can use the corollaries of Lagrange's theorem to calculate this. Mm, Either this one or that one. We need to consider modulo 11, okay, where 11 is a prime number. So we can use Fermat's little theorem directly, which is actually a particular case of Euler's theorem. So what it says, um, uh, one thing, this should be z minus 0 actually. Okay, so if we have a prime number and some a belongs to z minus 0, then a to the power p minus 1 will congruent to 1 modulo p. Okay, so we use this. We know that a to the power p minus 1 is congruent to 1 modulo p. If a belongs to z minus 0 and GCD of a and p, that is 1. Okay. So, yep, clearly 11 is a prime number and 21 and 11, they are co-prime. So we can apply this theorem. And this will give us 21 to the power p minus 1, that is 11 minus 1, that is 10, is congruent to 1 mod 11. Okay. Now we can use this one to simplify the given expression. Okay. Now 21 to the power 2026. This is equal to 21 to the power 202 into 21 to the power 6. Okay. Which is congruent to, this will be, okay, let's reduce it further. This will,
That power will
uh,
be
yep, I
2020.
missed it actually. Yes, 21 to the power 10 and then it's power 202. Okay. So this will be congruent to 1 to the power 202 into 21 to the power 6 modulo 11. Uh, Now is this clear?
On got it. Now 21, we can write it as -1 by
Exactly.
mod 11.
Okay. And this will be equivalent to 1 modulo 11. Okay. So the answer is 1 here. Now, this is actually another form to ask this. What will be the remainder when we divide 3 to the power
Is it
256 by 5?
3?
Mhm.
3. It is 3. remainder.
Okay, let's calculate. 3 to the power 256 modulo 5.
Wrong. Actually,
Okay, we need to consider this, right? So how to do it? Again,
we'll take the totient function or
yes,
by
here 5 is a
256
prime.
will divide by 4.
And GCD of 3 and 5 are 1.
It is 1. It is
So,
1. 1, 3 power 0, it will come.
okay, this is 1 again. Okay. So 3 to the power 5 minus 1 actually. This will be congruent to 1 mod 5, or 3 to the power 4 is congruent to 1 mod 5. Therefore, uh, yes, 3 to the power 256 is equal to, yeah, we won't get another power of 3 from here. Fine. So, uh, can you complete this? This will be 1 itself. Okay. Any doubt?
No, ma'am. Actually, 3 power 4, whole power 64 comes out to be 3 power 256.
Yes,
So
yes.
3 power 4.
This will be equal only. This will be congruent to 1 to the power 64 mod 5. So this will be 1 mod 5. Okay. Now what will be the value of this? So I think you can,
Uh, yeah, here we have to apply Euler's one,
yes,
Euler torsion function because it is
yes,
not prime. 100 is not prime.
yes,
But
here,
117 and 100 are co-prime to each other. So we can apply that part, no? Torsion function of.
yes. This is fun. Uh, we know that if A belongs to Z minus 0 and GCD of A and N, that is 1 for some natural number N, then A to the power phi N, this will be congruent to 1 modulo N. Okay, we can use this one. So from this, we can say that 117 to the power phi of 100, this will be congruent to 1 mod 100. Okay, now what is phi of 100? So how to
It is
calculate this?
40. It is
Mm,
40.
yes, I
We
guess
can.
so. So actually to calculate phi of 100, we need to consider prime factorization form of 100. Okay, so that
100,
is,
100 into 1 minus 1 by 2 into 1 minus 1 by 5 because its prime factors are 2 and 5.
yes. Okay, so this will be phi of 2 square and phi of 5 square. Phi of 2 square will be 2, and sorry, what will be this? Phi of 5 square. This will be, what is phi of p to the power k? That is p to the power k minus p to the power k minus 1. Right? So this will be 5 square minus 5. That is 20. So yeah, that is 40. Or you can say that 117 to the power 40 will be equivalent to 1 under modulo 100. Now, how to do this power 1 to 0 to reduce this using 40. So, can you calculate this? I
Yeah,
guess this is
yeah,
easy
yeah.
one. Okay.
117 square it comes out to be when we take the power
Wait. One
1202.
more thing you can do actually. This 117 can be reduced in 17 first for simplicity actually.
Yeah,
Okay, that will make the calculations easier.
yeah.
Okay, so
Then we
I guess
can take the
17,
3 power on the both the sides. So it will be 1200, 17 power 1200 mod
yes,
1, and then 2 is left. So 17 square,
17
which is
square.
289, and then
That is
289
89.
further mod 100, 89.
Mm-hmm.
So
Okay,
it
the answer is 89 actually. Now, what is the last digit of 7 to the power 73? So, this sort of
mod 10
questions
we have to
actually,
do.
yes. So, if we,
Last 10 digit mod 10.
yes, last digit means mod 10, last two digits means
Mod 100.
mod 100. Okay. And like if one will ask what will be the unit digit, like unit place, so that will be last digit. What will be the digit at like tens place? So that will be like first you will calculate last two digits and then this one like second last. Okay. So these are some questions which usually asked in competitive exams. So what we need to find here 7 to the power 73 mod 10. Okay, 10 is not a prime again, but GCD of 7 and 10 is 1. So you can apply the Euler's theorem and 7 to the power 5 of 10. What is 5 of 10? That is 4. This will be congruent to 1 mod 10. Now using this, you can reduce 73. So up to 72 you can write as
It
power
will
of
be
4.
3. Uh, Answer is 3.
Uh,
Because 7 result will be 7, then 7 again we have to go by mod 10.
so what is the problem there? 7 mod 10.
No problem.
So what will
Uh,
be the answer?
7.
7, no,
7.
not 3. Uh, you all can do this? Vaibhav,
Yes, ma'am.
it is clear?
Yeah, yes, ma'am. It's clear.
Okay, okay. So these are some calculative questions from number theory. Now come to the abstract part again.
Ma'am, like
Mhm.
what we have for the this permutation group or alternating group. I think same thing is the alternating group also, no? Permutation
Uh,
group.
yes, but first you need to study what are cycles, what are cycle decomposition.
Okay, so that will
Are
come in
you
the further
familiar?
syllabus. No,
Uh,
I'm not familiar with anything.
ac
Actually,
okay.
I
Yeah, I
lack totally
thought to
concept.
make a video actually, but I was just
Is it
waiting
there?
like
Is it there in the upcoming videos? This lecture, this one, cyclic
uh,
group, cyclotone, something like this.
mm, actually I can include the topics as either some counter to serve some counter example or to
Um,
prove some result.
okay. Like, ma'am,
Okay,
I'm
but
facing
concrete
a lot of
construction.
okay. Like I'm facing the problem in the like normal subgroups. Like some actually that
Okay,
concept also I
yes.
totally lack. Like when how to decide whether that all the cosets, whatever the cosets will form, that will form in normal subgroup. And moreover, this
Okay,
permutation group is also there. I think it is used in the Galva extensions somewhere. They are using that how the roots are connected and how it is linked with the uh, cyclic root, nth root of unity, how they are interconnected, and which will be the Galva extension, which will be the Galva group, something like that. Actually, I was not understanding a single line of that. So
okay. So I can include the questions on those topics in upcoming videos.
okay. So, can you explain more like how we can decide like the whenever we see the group that the group is normal or not? Like I'm getting the
Okay.
definition, but actually when the problem it comes with the application parts questions, so
Mm-hmm.
actually
I
directly it is
understand.
mentioned it is normal. Like we don't have that much concept, so either
Okay.
we learn the things. Okay, okay, next time same thing will be asked, so we write the as it is, but what is going on? Actually, more clarity is not there over there.
Mm,
If you
okay, no
could
problem.
explain.
I can include questions on that.
Okay, ma'am. Thank you.
Okay. So first, do this question. I guess there will be some question on this. If not, there are some questions on cosets actually. For normal, I need to see if we'll be able to discuss some questions on normal subgroups, then fine. Otherwise, we will do in next problem solving session. Okay. So this one, and suppose we have a group, then a map from the group to itself, which assigns G to G square. This will be homomorphism if and only if G is abelian. Okay. So consider the function to be phi. So phi of phi from G to G defined by phi of G is G square for all G belongs to G. Okay, then phi is homomorphism if and only if G is abelian. So what is homomorphism? Uh, Actually group homomorphism. So a function will be group homomorphism if that preserve group operations, that is phi AB will be phi A phi of B. Like here the hidden star or dot, that is the group operation. So if this is true for all A and B belongs to G, then we say that phi is homomorphism. Okay. So let phi is homomorphism. Then we have phi of AB is phi of A into phi of B. Now we need to check G is abelian. So we need to consider AB, like AB should be BA. We need this. So what is phi of AB? Phi of AB is AB square by the definition. This is one. Okay. So AB square will be phi of A, phi of B. Or AB square will be A square, B square. Okay. Now AB square is basically AB, AB, and this is A, B, B. Okay. We can apply left cancellation law and right cancellation law, and then we will get BA is AB. And A and B were arbitrary, so we can conclude that G is abelian. Okay. What about converse? If G is abelian, then we will have AB and BA are same for all A and B belongs to G. Okay. Then phi of AB, that will be AB square by 1. That is AB, AB, but the group is abelian. So this BA, like here we use associativity actually. So this can be written as A, B, B. So this will be A square, this will be B square, and this will be phi of A, phi of B. So we conclude that phi is homomorphism. Okay. So if we have a function uh, from G to G such that phi of G is G square, then this will be homomorphism if and only if G is abelian. Next question. Let G and G dash be two groups and phi is a group homomorphism from G to G dash. Consider some element G in the group G and H, which is a subgroup of G. Then we have these two statements and we need to prove this. So phi from G to G is homomorphism. Then phi of Gn will be phi of G to the power n, which is actually obvious. Okay. Why? What will be phi of Gn? This will be phi of G into G. How many times? N times. But phi is a group homomorphism. So this will be phi of G into phi of G, phi of G n times. This will be phi of G to the power n. Okay. So this is a simple one actually. Second, if order of G is finite, then order of phi of G divides order of G. Okay. So let order of G is K. Okay. So what will be, we need to consider this order of phi of G means we need to consider this phi of G to the power K. This will be phi of G K by 1 and order of G is K. So G to the power K will be identity. So this will be phi of identity, which is identity. Okay. that is phi of g to the power k is identity, or order of pi of g to the power k, this will be less than or equals to k, and this divides k. Okay, means you can say that phi of g divides order of g. Now, next question. Under the same assumption, like G and G dash are two groups and phi is a group homomorphism from G to G dash, and H is a subgroup of G. So if we say that H is a normal subgroup, then phi of H is a normal subgroup of phi of G. Okay. Does it mean if H is normal in G, then phi of H is normal in phi of G? Okay. How to prove whether a subgroup is normal? So there are alternate definitions to prove a subgroup to be a normal subgroup. We can either use this one, or any condition from this, or we can simply use this one. G inverse HG belongs to H. Okay. Or alternatively, we can use this also. GH G inverse belongs to H. They are same actually. Okay. Because this is true for all G belongs to G. So in place of G, we can write G inverse. Okay. So these two are also equivalent. Okay. So we are using this condition. G inverse HG belongs to H. If this is true for all H belongs to H and G belongs to G, then we say that H is a normal subgroup of G. Okay. So we need to consider some arbitrary element in phi of H and phi of G. So say phi of H belongs to phi of H, and phi of small g, this is in phi of capital G. Okay, where H is in the subgroup and G is in the group. Okay, actually phi H and phi G, they are images of H and G respectively. Okay, so they will be like you can say like phi will be phi will be surjective actually if you restrict the um, codomain to the image set. Okay, so every element in phi of H can be written as phi of H. Whenever you will have some, say X belongs to phi of H, there exists some H belongs to H such that phi of H is X. Okay, so using this, we directly consider phi of H in phi of capital H and phi of G in phi of capital G. Okay, so now what we need to consider to prove that phi H is normal? This phi of G inverse phi of H phi of G. Okay, like this G inverse H G, this belongs to H like this. Okay, and this will be same as phi of G inverse by because, okay, write it here only. Phi of x inverse is phi of x whole inverse. They are same. We can check this. Okay. And phi of h, phi of g will be phi of hg, as phi is in homomorphism. And again, this will be phi of g inverse hg. This will be in phi of h, as g inverse hg belongs to h, because h is normal in G. Okay. So you can conclude that phi of H is normal in phi of G. That is, phi of H is a normal subgroup of phi of G. This is actually the theoretical part. H and G, we assume them in abstract sense. That's why we use this theorem kind of thing to prove that phi of H is a normal subgroup of phi of G. Whenever we will have some practical examples, other than abstraction, there can be some like some tricks or some equivalent definitions to calculate the normal subgroup or to check whether this is normal or not. Okay. So we will cover that in either this or upcoming problem solving session. Till then, this question. Consider a statement that every finite group having more than two elements has a non-trivial automorphism. This is true or false? Let G be a group such that order of G is finite and order of G is greater than 2. It has at least 3 elements. Okay. Then will there be a non-trivial automorphism always? So we can have two cases actually. If G is non-abelian, what if G is non-abelian? So consider the map phi from G to G defined by phi of x is Gx G inverse. This is a map similar to inner automorphism actually. Okay. So this is for all x belongs to G. So actually here we fix G. So we can say there's phi G also. And okay, keep this in mind. Order of G is greater than 2. So yep, this is well defined actually. Now we can check that phi G is a group automorphism. Okay. When will you say a map to be a group automorphism? This must be well-defined map. This is 1, 1 onto and group homomorphism. Okay. So phi G is well-defined as if you have x equals to y in G, then Gx G inverse is Gy G inverse. Like if you multiply G by left and G inverse by right, then you will get Gx G inverse is Gy G inverse for all x and y belongs to G. What does it mean? It means that every element in G has a unique image. Okay, it cannot have more than one images, so the map is well defined. Secondly, phi G is 1 to 1. This is injective. It means, again, you need to consider two elements. So let x and y belongs to G. If phi of x is phi of y, that is, if images of two elements are equal, then what will we get? First of all, this will be Gx G inverse is equal to Gy G inverse by the definition of phi. By left cancellation and right cancellation law, okay, you can get x equals to y. Okay, it means the map phi G is 1 to 1. Then phi G is onto. How to check whether this is subjective or not? Okay, so to uh, you need to consider an element in the codomain part. Let's say x belongs to G, then there exists G inverse xg belongs to G. Here we are taking codomain 1 and here we are taking domain 1 actually. Okay. Such that phi of G inverse xg, that is phi image of this element, this will be G, the element, that is G inverse xg, then G inverse. Use the associativity, you will get G inverse x, here it will be G inverse. Now G and G inverse are inverses of each other, so this will be identity. And this will be x again. Okay, so you can say that phi G is onto. Now phi G is group homomorphism. So how to check that? Again, we need to consider two elements. X and y belongs to G. And what is phi G of xg? That is G, this is y. The element, that is xy, and then G inverse by definition of phi G. This can be written as G x, here identity, y G inverse, which can be G inverse G, y G inverse. Okay, but you can use associativity here. Okay, and this will be phi G of x, phi G of y. So you can conclude that phi G is an automorphism. Okay, it means whenever you will have a non-abelian group, you will have an automorphism. But is that non-trivial? So If phi g is trivial, then phi g is same as the identity, that is phi g of x is same as ix for all x belongs to G, or Gx G inverse, this will be x, or like you will multiply by G from right and then you will use the identity. So this will give you Gx is xg, okay, for all x belongs to G. Which is not true. Okay. Why? Because G is non-abelian. Therefore, phi of G is non-trivial. Okay. See, this is possible that for some G, you can have phi of G is identity, but not for all. Okay. I'm saying that this can be true that phi of G is identity, or Gx is xg for all x belongs to G for some G. Actually, if G is identity, this will be true. Okay. So you need first you need to choose the element G to make this automorphism phi G different from the identity element. And if you are aware with the concept of center of a group, then you need to exclude this G from the center of G also. Center of G means the collection of uh, those elements which commute with every element of G. This is basically a part which is abelian. Okay. So if you will not be able to find any G such that you can define phi G, uh, other than non-trivial one, then your G will become abelian. Okay, then you will get a contradiction. So there will be at least one G such that phi of G is a non-trivial automorphism. Okay. So with this, you can conclude that the statement is true if G is a non-abelian group. Now, what if the G is an abelian group? Okay. So second case, if G is abelian. There can be subcases also. So say subcase 1. Why we are considering these cases and subcases? Because uh, we don't need to find just an automorphism. We need to find a non-trivial automorphism. Trivial one, that is the identity, will always be there. But what about non-trivial one? So that's why we need to separate the statement in different categories. Okay. So the case 2 is if G has an element of order greater than 2. Okay. Till now, we have the assumption that G has number of elements more than 2. G has at least 3 elements. But now we are considering the subcase that G has at least one element which has order more than 2. That is some element of order 3, 4, or uh, any number greater than 4. Okay. So in this case, we can consider another function, say pi, or let's use some another notation, say tau, from G to G, defined by tau x is x inverse for all x belongs to G, then we can prove that tau is an automorphism. Okay. So can you do it? Like we are assigning every element to its inverse under the map tau, and inverse is unique, like inverse of every element in a group will be unique. So tau x will be well defined and this will be a one-to-one map. This is obvious, okay? And for any y belongs to G, there exists y inverse belongs to G such that y inverse, or like tau of y inverse, this will be y. So in this way, you can say that tau is onto, okay? And using two facts that xy inverse is y inverse x inverse and G is abelian, you can prove that tau is homomorphism also. It means this is easy to check that tau is an automorphism. So can you do it? Can you check that tau is an automorphism? Or we need to do it? Can I leave it? Students?
We'll try, ma'am. Do.
Okay. But we need non-trivial one. Okay, so we need to check that tau is non-trivial. So what if tau is trivial? Tau will be trivial if this is same as the identity or tau of x is I of x for all x belongs to G, or x inverse is x for all x belongs to G, or x square is identity for all x belongs to G, right? Or we can say order of G is 1 or 2 for all x belongs to G. X square is identity means order of x. Sorry. Order of x can be either 1 or 2 because order of x will divide 2 in that case. Okay. But we consider that G has an element of order greater than 2. It means this is a contradiction. So tau is non-trivial. Okay. So if G is an abelian group and it has an element of order greater than 2, then again we can have a non-trivial automorphism. Now only one case is remaining, and that is if G has no element of order greater than 2. That is, G has elements of order 1 and 2. There will be a unique element, and that is the identity one of order 1. All the other elements will be of order 2 in this case. Okay. So G will be isomorphic to Z over 2Z cross Z over 2Z, or we can write it as Z over 2Z power n. Okay. Or n is greater than 1. Okay. N cannot be 1 because if n is 1, then G will be isomorphic to Z over 2Z. That is, G will have only two elements. Okay. Now, suppose, okay, construct a map. Say this is rho from G to G, defined by rho of x1, x2, xn, uh, z over z2 to the power n means mm, n times product. So we will have an n tuple. So to define a map, we just swap any two elements, say first and second one. So this is x2 and x1, and all are fixed. Okay. And this can be done as n is greater than or equal to 2. So this map rho is a non-trivial automorphism. Okay. So we get a non-trivial automorphism in each case. So the statement is true. Okay. Is it clear? You will consider three cases. If G is non-abelian, then inner automorphism will be the non-trivial automorphism. If G is abelian and it has an element of order greater than 2, then the inverse map will be the non-trivial automorphism. And if G has no element of order greater than 2 and G is abelian, then this will be a non-trivial automorphism. Therefore, the statement is true. Okay. Now, this question, product of two subgroups is again a subgroup. So, is it true or false? Means let G be a group and H1, or say, fine, H1 and H2 be subgroups of G, then is H1, H2 a subgroup or not? Is it true? Or we can have a counter example. So, are you familiar with dihedral group? Dihedral group of degree n or order 2n?
A dihedral group is related to the polygons.
Yes.
Mhm.
So we can find counter examples in Dn. Consider D4. What is D4? This is dihedral group of degree n and order 8. Okay. Degree n means this will be the group of symmetries of squares. Okay. And it will have 8 elements. consider this, say H1 is R naught, which is the rotation by 0 degree, and say H, that is reflection about the horizontal line, and H2 is R naught, and say D, that is the reflection about the diagonal. So H1, H2 is not a group or subgroup actually. Subgroup of D4. So can you check this? Do you know what is the meaning of H and D here? How we define this? See, we have, I want to give a quick construction for this. Symmetries of regular polygon of degree 4 means squares. Okay. So you can suppose this like this. Say this is A, B, C, and D. Like it has the vertices A, B, C, and D. I'm labeling the vertices so that uh, we can imagine or we can understand the reflections and rotations here. Okay. Now in D4 or in D in general, we have two types of elements. First is rotation, second is reflection. Okay. So rotation means we rotate it by an angle so that the symmetry doesn't change. Okay. So if we have a square and someone asks us, like we want to rotate it by some degree such that it will remain a square with this orientation again. So that will be 90 degree, minimum 90 degree. Okay. I know, like if we rotate it, then vertices will be changed, like they will change their position, but the symmetry will be preserved if we rotate it either by a degree of 90 degree or some multiple of it, okay, in clockwise or anti-clockwise. So let me fix it in anti-clockwise for simplicity, okay? Rotations in anti-clockwise directions. Okay, so we consider this R0, R90, R180, R270. It can be written as R1, R2, R3, R4, or sometimes like R0, R1, R2, R3. There can be different um, notations for this. So what does it mean? R naught means we rotate the square by 0 degree anti-clockwise. Okay. So R naught will be, okay, let's increase the size. This will be A, B, C, and D itself. What is R90? This will be rotation by 90 degree. So A will come here, A, and then B, C, and D. R180 degree means we rotate it anti-clockwise by 180 degree. So A will come here, then B, C, and D, and R270. So that will be A, B, C. Okay, sorry, not this. A will come here. A, B, C, and D. Okay. What if we rotate it by 90° in anti-clockwise direction again? We will get R naught. Okay. So we fix this element as the identity one. Okay? Because this is this is correspond to no change in the given square. Okay. We didn't change its symmetry actually. So these are four kind of rotations. So here, what is the operation actually? Operations mean we are rotating the square. What about R? Okay. Order of R naught. Order of R naught will be 1. What will be order of R90? Order of R90 means
Four.
what is, yeah, this is 4 because we need to rotate it like 4 times. If we rotate 4 times by 90°, we will get the square in that's original position again. Okay. So that is 4. Now what is order of R180? So that is 2. Okay. If we rotate this by 180° again, then A will come here. Okay. And similarly, R270, this is 4. Okay. So these are 4 rotations. There are 4 more elements and they are reflections. And what they are, uh, we generally represent them as H. Fine, I write here H, V, D, and D dash. Okay. H means horizontal, V means vertical, D means diagonal, and D dash means anti-diagonal. So we have the original square as A, B, C, and D. So this will be the horizontal axis. If we reflect the vertices about this, then we will get AB here and DC here. Okay. What if we use vertical reflection like this? Then C and B will come in left side and A and D will come right side. Okay. So this will be C, B, A, and D. Now what about this will be the diagonal one and this will be the anti-diagonal one. Okay. So for diagonal one, we will have A, B, C, and D. This is the diagonal. So if we reflect about this, so A and C will change their position. B and D will be remain unchanged. Okay. So B and D, no change in their position. Here C and here A. Okay. What about D dash? So now anti-diagonal. So A and C will not change their position, but B and D. So this will be B and this will be D. So these are 4 reflections. And you can check that all has order 2. You can find another notations, another representation in different books. This is one of them. Okay, so these are the elements. And now what we are doing, H1 is R naught H and H2 is R naught D. So if H1 H naught is a subgroup, it will be closed. It means H, D, this must be in second. Uh, Okay, let's construct this. What is H1, H2? So H1, H2, we will have R naught in this, we will have H in this, we will have D in this, we will have powers of H and powers of D in it, but H square will be R naught, D square will be R naught, so powers are already there. We need to check H, D and DH, what they are. Okay, and we write those elements here, and then we need to check whether uh, that will form, like that set will form a subgroup or not. So you can check this is not closed with respect to this operation. So this is a counter example. We are running out of time, so I'm leaving this for you. You can check this, and from this onwards, we will continue in next session. Any doubt? But yep, I would like to define what is HD. What is HD actually? You will like, if you are not fluent with this, just start with the square, that is A, B, C, and D. First apply D on it, then apply H on it. So uh, when you apply D with it, you will get A and C, B and D, and then H. So you will get H means this. So this is A, B, this is D, and this is C. So this is actually rotation by 90 degree. This is R90. Okay, so HD is R90. This is how we define this. Okay, so R90 will be there. Then you will calculate what is DH. Okay, what is DH means, first you take horizontal reflection, then diagonal one, and you include that element in H1, H2 again, and check whether that is a subgroup or not. Okay. Uh, One thing, whenever you multiply rotations, Ri, Rj, you will get another rotation, Rk. So no problem. But for reflection, you will get rotations also. Okay, so first you need to construct the composition table for simplicity, and then you can compute what is H1, H2. And H1, H2 is not a subgroup of D4. Okay. In next session, what we can do, we can discuss all the possible subgroups of D4. Okay, so that will help you to figure out why H1 and H2 cannot be a subgroup of D4. Okay, so until then, I'm leaving for you. You will construct what is H1 and H2 in next session. In general, we can discuss the structure of subgroups of D4. And then we can also verify that H1 and H2 is not a subgroup. So, yeah. Any other doubt?
No, thank you, ma'am.
Okay.
No,
Thank you. Yes.
Yeah, ma'am, thank you.
Okay. Thank you.
Thank you so much, ma'am.
Okay.
Very nice explanation.
Thank you. So I'm
good night, ma'am.
okay. Good night. Let's meet in the next session.